Okay, let's get started with class. So hopefully everyone enjoyed the day off on Wednesday. And if you didn't have class on Thursday, like me, or at least I don't have to teach class, you had like a weekend inside of the weekend. It's rather nice. And then we finish today and then you have another weekend. So I guess like the big news, I mean, yeah, I'll be talking about like section 2.3 and 2.4 today. But really like the big news is that the exam is going to be Friday of next week. So you should have gotten an email from me, I think on Tuesday, where I sent you the exam review. It's like 15 or so problems, just going over the stuff you need to know from the first two chapters. So we'll go over the exam review in Wednesday's class next week, or maybe Monday. I might switch things around. I don't know. We'll see where I click on that. But we'll probably go through the review on Wednesday of next week. I'll post the solutions online. And then over the weekend, I'm going to post the solutions to all the homework problems and all the quiz problems as well. So those would be good to look through. I graded quiz 3. I plan on going through some. I'll probably go through quiz 3 on Wednesday as well. It's like quiz 3, there's a lot of difficulty with it, where I didn't really intend for there to be difficulty. So it'll be good to go through. I'll pass those back at the end of class today. But yeah, that's kind of the summary. What next week is going to be looking at. Right now, you should be focusing on studying for the first exam. There's no homework due next week, so you don't have to worry about any homework assignments or anything like that. So just focus on doing the exam review is what I would say. And so there's two sections we still need to complete before for the exam, right? There's sections 2.3 and 2.4. So we started section 2.3 on functions on Monday. So we talked about like what it means to have a function, how are they defined, what it means to have a one-to-one function, what does it mean to have an onto function, et cetera, et cetera. So we ended up going into inverse functions. This is where we left off. And so I'm going to go through it. I'm going to go things a little bit faster today, just because there's a lot of material that needs to be covered.
So well, sir. I hope things go well today, sir. I think I forgot to remind us anything about the homework assignment. So it was late last night when I remembered it.
Yeah, okay, we can talk about this later. So we're going to go through functions. We're looking at inverse functions and composition of functions. And so as a reminder, in order for an inverse function to be defined, the function f needs to be one-to-one. Otherwise, you have a situation where you have two different inputs that map to the same output. But then if you're going to imply the inverse to the output, you can't really determine like, should it go to x1 or should it go to x2, right? It would have two outputs and then the function wouldn't be defined. So you need the function to be one-to-one. And then you can look at this diagram to get an intuition as to what's going on with inverse functions. We talked through it in class on Monday, so I'm not going to do it now. Let's see. So we'll go through these two examples. So I don't know how important it's really going to be in this class to be able to calculate inverse functions, but we'll go through at least one example. This is something you probably have been exposed to in like a, I don't know, like a 10th grade or like a algebra class in the past. So we're going to assume we have a function f that maps z to z that's given by f of x is equal to x plus 1. Oh, let me make sure I'm recording. I do this like every single day, but okay. I need to have more trust in myself. We are recording. Okay. So we have the function f of x is equal to x plus 1. And then the first question is f invertible? And if it is, what is its inverse going to be? And so to determine whether or not f is invertible or not, we need to determine whether or not it's going to be one-to-one. And so how you determine whether a function is one-to-one or not is you're going to suppose we have two elements a and b. So we're going to suppose we have f of a is equal to f of b. So we're saying that a and b have the same output. And so to show that this function is actually going to be one-to-one, we need to show that a has to be equal to b. Right? And so if we have f of a is equal to f of b, we've defined the function to be equal to x plus 1. So f of a is going to be equal to a plus 1. F of b is going to be equal to b plus 1. And so if we need to show that a is equal to b, I mean, we just subtract both sides by 1, right? If we subtract both sides of this equation by 1, this then gives us a is equal to b. right? So we showed that if f of a is equal to f of b, then we have to have that a is equal to b. This implies that f is 1 to 1, which I'm going to write like this just for convenience. So this is the same thing as saying it's like 1 to 1 or injective. And then from here, you can say something like thus the inverse exists. So f inverse of x exists. Right, so this is a concrete example on how you can show a function is going to be 1 to 1. If I ask you to show something's 1 to 1 on like a quiz or an exam, like these are the steps that you need to take. Like you can't put it in like words, you actually have to do like the computation to show that at the end a is going to be equal to b. And so we know the inverse does exist, and so we need to find what the inverse is going to be. And so this is probably the part that's going to be more familiar to you from previous math classes. So what we're going to do is if we want to find f inverse of x, what this means is we're going to set y equal to our function. So this is going to be y is equal to x plus 1. And then all we do to determine the inverse is we have a function y in terms of x. We're going to rewrite this so that way we have x is in terms of y. So we're just going to subtract both sides by 1. So we have y minus 1 is equal to x. And then we're just going to define the inverse to be the input minus 1. Right? So this implies that we have that if f inverse of x is equal to x minus 1. Where the minus 1 just comes from what we have here. I know it says y minus 1 here, but we're just going back to the original variable we were working. Right? So this y minus 1, we just write it as x minus 1. Like the fact that we're changing the variable doesn't really matter. So this would be the inverse function. Right? So the general steps, again, we're not going to do this too often, so I'm not going to write out like all the steps because I'm not going to ask you to do this in the future probably. But so like you set y equal to your original function, and then you solve for x, and then whatever x is equal to will be your inverse function, is the idea. Again, I'm more so interested in what you can do with the inverse and finding the inverse itself, but it's good to go through at least one example. Okay, any questions about this? Okay, and then this is another important example that you kind of have to know. This is like your fundamental counter example when you're thinking about a function that's like either 1 to 1 or not 1 to 1. So for this example, it says let f be a function from R to R, be the function f of x is equal to x squared. I'm just going to ask you, like, is f invertible? Does anyone know? Like, will f be invertible here? Yeah, go ahead.
Would it perhaps be a f inverse of x equals the square root of x?
Not necessarily. If you restrict your domain, then it is possible. But if you're including all the negative numbers, there's going to be issues, is what I would say. Yeah.
It's not.
Yeah. So we saw before, and like the same problem we saw in the past is going to show up here as well. I don't remember exactly where we talked about this, but oh yeah. So like on page 2 of the notes, right, we said that the function f of x is equal to x squared is not 1 to 1. So for instance, we have like f of minus 1 is equal to f of 1 is equal to 1 because minus 1 squared is equal to 1 squared. And so if you took the square root of 1 as like your inverse, you wouldn't know like whether or not you're going to be going to like minus 1 or actually there's a better way of wording this, but like the issue is like the function is not going to be 1 to 1. And so if you like squared the square root, you'll get like plus or minus 1, right? So the answer is going to be no for this one. You could make it so like if you restrict your domain to the positive integers, then the function is going to be invertible, which is something we'll see in the future. But the issue is like f is equal, or I should say f of x is equal to x squared is not invertible on the real numbers. Or I should say, sorry, I'm like, it's 8 o'clock in the morning. I'm gonna make mistakes. So this is, it's not 1 to 1 on R. So it's not going to be invertible. right? Like the question being, like the issue is going to be for problems such as like, what would like f inverse of 4 be equal to, right? Because you have two different points that map to it. You have -2 and 2 both map to 4, so this like wouldn't be well defined. Any questions about this example? Okay, and then the other operation, maybe I'm going like a little bit quick, but I need to get into like sequences and sums. So the next operation,
Did you write f inverse of 4 be equal to?
oh yeah, I should have like what? Sorry. And then like a question mark. Yeah, so what would f inverse of -4 be equal to? Right. And so we have the next definition. This is the other operation you need to be mindful of. And it might be the more important operation, to be completely honest. So this is looking at the compositions of two functions, which is also something you've probably seen in the past, but I definitely need to go over it at least once in this class because it's going to be important. So we're going to suppose we have two different functions now, f and g. So we're letting f be a function from the set A to the set B, and we're letting f be the function from the set B to the set C.
You said f for both times.
Oh, I meant g. So the composition of the functions f and g denoted for all a and a, so little a and big A, by f composition, or f circle g is how I'm going to be saying this. This is going to define a new function from A to C defined by the following. All right, so this A exists within our initial set A, and then G is going to take it to B. So G of A is an element of B. And then if you apply F to G of A, this is now going to be an element of C, right? So if you compose the two functions, this is really going to be a map from the initial set A to the set C, which is illustrated in this image, right? So this is our G of A going from the set A to the set B. This is our function f going from the set B to the set C. And so composition is really just like jamming them together in a sense, right? So it gives you a way of kind of like skipping to the end, right? Going from A to C by combining them. So if you see f circle G like this, it just means that you're applying f to whatever G is equal to, right? So like you take your G and you make it so it's the input of whatever your f function is going to be. And of course, we're going to look through some examples, and it's probably better to just understand like how to work through the examples. If you understand how the examples work, then you can use that to understand more general abstract ideas involving the composition. So there's two examples I wanted to go through. So the first example, this is kind of a generic problem where we have f and g are both functions from the set of integers to the set of integers defined by f of x is equal to 2x plus 3 and g of x is equal to 3x plus 2. And so a basic question can be something like, what is the composition of f and g? And then you can go backwards, right? What is the composition of g and f? And you should, I mean, if you've been exposed to compositions in the past, you should kind of already know that like the composition in one direction will be different from the composition in the other direction. Right, so if I wanted to compose f with g, this is the same thing as applying f to whatever the image of g is going to be. This is just the definition of the composition. So we're told in the problem statement that g of x is equal to 3x plus 2. So this is going to be equal to f of 3x plus 2. Just substituting in the definition we had for g of x in the parentheses that we have here. And so if we have f of 3x plus 2, what this means now is we look at our function f, and wherever we see an x, we're just going to replace it with a 3x plus 2, right? We're just taking 3x plus 2 as our input now. So this is going to be equal to 2 times 3x plus 2. And then this is going to be plus 3. Right, again, all I'm doing is substituting in for this x our function g of x because we're doing f of 3x.
Simplify from there.
Yeah, well, I mean, that's what I'm going to be doing. So this is going to be equal to, well, let me erase this. I don't know. Oh, yeah. Sorry. So this is equal to, like if you did 2 times 3, that's going to be 6x. And then we have 2 times 2 plus 3 will give you a 7. So this is 6x plus 7. So that's how you find the composition of two functions. And I can give you like more complicated examples, but the process remains the exact same. Like ideally, if you can do this example, you can do any example. It doesn't really change all that much, even if I gave you like weird trig functions or what have you.
The order of G and F is important, as shown by the next part.
Yeah, that's true. Yeah, so again, we go through this exact process over again. So now we're going to do G composed with F. Again, by definition, this is really just G applied to F of X. So this is going to be G, and then we just plug in. We have F of X is equal to 2x plus 3. So this is G of 2x plus 3. And we apply the exact same. Oh, I hate it when I do that. I don't know how to bring it back. Yeah. Whatever. I'm going to live with it. So this is going to be equal to. So we have G is equal to 3x plus 2, and we're choosing our input to be 2x plus 3. So wherever you see an x with G, you just replace it with a 2x plus 3. So this is going to be equal to 3 times 2x plus 3. And then this will be a plus 2 here. And so you can perform the multiplication. We have 3 times 2x will give you a 6x. And then you have 3 times 3, which is 9 plus 2, which will give you 11. So this will be plus 11. Yeah, so hopefully that's not too bad. Let me see if I can. It's driving me crazy that it's like this. I don't want you guys to want me to figure this out for 5 minutes. So, okay, I'll just, we'll live with it. Okay. Any questions about these two examples about finding the compositions of two functions? Okay, yeah, so this is something you need to know how to do. I would say the composition is going to show up more frequently than the inverse. So maybe I should have had the composition before the inverse, but whatever. Okay, and so this next example is going to illustrate how you can think of the inverse in terms of a composition of two functions. Right? The idea being that if we take the composition of a function with its inverse, it should go back to whatever the original element is going to be. And so for this next example, we're going back to what we were looking at before, right? We're looking at the function f of x is equal to x squared, except now we're going to be making restrictions to making it so the function has a well-defined inverse. So we're going to have two different functions, f and g, be the functions defined by first f, where f is a function that goes from r to the positive real numbers, with f of x is equal to x squared. So again, now we're restricting what the codomain is going to be to make sure our numbers are well defined. When we take this, well, when we apply the inverse, and then we have that g is a function from the positive real numbers to r defined by the square root. And so it's just going to ask, what is the composition of f with g? And this is what Nico was getting at earlier, right? So if we do f of g of x here, we have that g of x is the square root, so we have f of the square root of x. And then we have that f of x is the square, right? So this is just going to be equal. F of the square root of x is defined as the square root of x squared, which is just equal to x. So the main takeaway is when we compose x squared with the square root of x, like we did here, we take our original input x, and that ends up being the output of the composition. So like the input remains being fixed, right? And then we can go the other direction as well. And you should expect the same thing to happen if you do g of f of x. This is going to be g of x squared. G is the square root, so this is the square root of x squared, which is just equal to x. Again, the main point being, if you compose these two functions, in this instance, the order doesn't matter like we had before. So before we should have seen f of g and g of f end up giving different outputs, so they're different functions. Whereas here, these two compositions are equal, and it just ends up being whatever the original input was. Oh yeah, question.
function, or do we just set it like that? Because it would have to be only positive numbers, and the range would also be only positive numbers.
Yeah, I think I was misspeaking before. Like when I was talking about x squared in the past, I think I was talking about the domain when I should have talked about the codomain. Like the issue with the inverse before, man, all sorts of problems. Let's see. Yeah, it just crashed on me. Hopefully it's not going to be a recurring issue. The issue we had before when we were thinking about one-to-oneness was the fact that we were including, like if we were looking at this example, we were looking at f from R to R. And so the issue we had before is if we define an inverse function going from R to R, you can't take like a square root of a negative number. That was the real issue. I kind of misworded it when I was describing this in the past. In order for the inverse to exist, you have to make like this restriction on the codomain. So that way, when you take the square root, like you're only taking positive numbers because you can't take the square root of a negative number. Am I answering your question, or am I
Yes,
missing it?
do we have to like specify that in our answer, or is it fine because it's in the?
Oh yeah, it's fine because it's mentioned in the actual problem statement. It's fine. Like you wouldn't have to have any writing, like in your own answer because it's giving you what the domain. Any questions? Any other questions about this example? Okay, and so the main point for this example is that if we have f of x is equal to x squared, then in this instance we have that g of x, which is equal to the square root of x. This is really equal to the inverse of x. Because if you perform the composition, it's like the two are canceling out with one another, right? It's almost like when you do f composed with g, they cancel out and you're just left with what you originally. And so I go into a little bit more detail here at the bottom. So when the composition of a function and its inverse is formed in either order, you end up getting what's called an identity function, where an identity function is just a function that maps an element to itself. So when I say identity function, it's like a function I such that if you do an input x, it just outputs x over again. It doesn't change anything with the input. So that's what's going on when you do f composed with f inverse of x. Or if you do f inverse composed with f. The order doesn't really matter when you're thinking in terms of inverses. Yeah, and so this is kind of what I was illustrating at the bottom here, right? So if you compose the inverse of f with itself, you end up just getting the original input, vice versa here. And so you have I don't know, I feel like I'm just like, this writing is just exactly what I've been saying, right? So it's something to keep in mind for the future. If I want you to show something's an identity or an inverse to another, you just take the composition and show it ends up being what's called the identity function, is the idea. So this is what you would want to reference. Any last questions about functions before we move on? Okay, the last thing that's going to be on the exam is going to be sequences and sums. And so if you take in Calc 2, maybe you're afraid of the word sums because you do like a bunch of stuff with like infinite sums and it's kind of nightmarish. It's everyone's least favorite part of Calc 2. I can't speak for everyone, but it's most people's least favorite part. So but I will say, like, if you've done Calc 2, the sums in this class aren't going to be bad because we're doing like discrete math. So we're not going to be focusing on infinite sums. We're going to be working with finite sums. And you're not going to have to do any calculus. So if you've done calculus 2 sums, this is going to be easy for you. That's what I'm getting at. But we are going to focus on sequences and sums. So these are two very important notions or ideas that are going to show up if you're doing any sort of programming or really anything involving mathematics. And so what is a sequence? A sequence is just an ordered list of elements. These are going to be used in discrete math in a number of different ways. So for example, they can be used to represent solutions to certain counting problems, as we'll see in chapter 8. They're also important if you're working with like data structures and computer science. Like if you think about like a binary bit or like a binary string of bits or whatever, it's like really just like a sequence of like binary inputs. So if that's like a sequence and that's a fundamental object you care about in computer science, like sequences must be somewhat important. So we often need to work with sums of terms of sequences in our study of discrete math, or if you're doing like anything involving statistics, sums are going to be ubiquitous. So this section reviews the use of summation notation as well as basic properties of summations and their formulas. But first, before talking about sums, I have to talk about sequences. So a sequence is a discrete structure used to represent an ordered list. So for example, if you have the following collection of numbers, 1, 2, 3, 5, and 8, this is a sequence with 5 terms, because there's 5 numbers. And then you can also have an infinite sequence as well, right? So this is a sequence that goes on forever. So you have 1, 3, 9, 27, 81. The general ruling here is that we're just taking powers of 3. For example, 3 is 3 to the first power, 9 is 3 squared, 27 is 3 cubed. So the general term is just written as like powers of the number 3. So this is an example of an infinite sequence because you can just let n increase arbitrarily. So the formal definition of a sequence, so we can define a sequence in terms of functions. Now that we know what functions are, we can talk about sequences as a function. And so what a sequence really is that a sequence is a function from a subset of the set of the integers, usually either the set starting at like 0, 1, 2, up into infinity, or the set beginning at 1 and then going to infinity, so like the positive whole numbers, to some set x. And so we use the notation a sub n to denote the image of the integer n. And then we call a sub n a term of the sequence. And so we use the notation using the set brackets about this sequence, a sub n, to describe a sequence. And so, I mean, I'm describing a sequence in terms of a function from the set of the integers or a subset of the integers. So what I'm saying is like, what this function is, and I'm probably not going to ask you this in the future, is like we're really taking a function that goes from the integers or subset of the integers to a set S, where we're taking the integer n, and then we're sending it to the nth term of the sequence. This is the function that they're describing in the definition. You're probably not going to have to make use of this, but I just wanted to clarify what it means by saying a sequence is a function, right? What's going to be important in this class, I say this over and over again, is actually computing examples. Like it's good to know the definitions, but it's more important to understand like how it shows up or like what it actually means when you're given a problem. And so for this example, it's asking you to find the first 4 terms of the sequence a sub n, where we have that a sub n is defined to be n plus 1 to the n plus 1 power. And so you just want to go step by step, right? So if we want to find what a sub 0 is going to be, if we're looking at a sub 0, this means that the nth term is going to be given by 0 plus 1 to the 0 plus 1 power. So this is going to be equal to 0 plus 1 to the 0 plus 1 power. Right, so you just take your n. In this case, n is equal to 0. So in this case, our n is 0. So this is going to be n plus 1. So 0 plus 1. And then the power is to the n plus 1 power. Again, n is equal to 0. So it's 0 plus 1. So this is really equal to 1 to the 1 power, which is equal to 1. So that's the first term of a sequence. And then you just follow the exact same logic, right? So you have a of 1. In this case, our oh yeah, there's no quiz today. We have a sub 1 implies that n is equal to 1. So you do like 1 plus 1 to the 1 plus 1 power. This is 1 plus 1 to the 1 plus 1 power. This is really the same thing as 2 squared, which is equal to 4. And then you just keep on going, right? So if you do a2, this is going to be, so in this case, our n is equal to 2. So you just plug in n is equal to 2. So this will be 2 plus 1 to the 2 plus 1 power. This is equal to 3 cubed. This is equal to 27. And then the last one, maybe it's getting tedious at this point, but it's good to know like how to do all these examples. This will be 3 plus 1 to the 3 plus 1 power, which is the same as 4 to the 4th power, which is equal to 64 times 4, which is equal to 256. right? Once you know how to do one, all of them are kind of similar to one another, right? You just plug in a different number at the end of the day. Is this confusing to anyone? Like, are there any questions about how I'm getting these terms like A0, A1, A2, A3? It's only going to get more difficult. So if you have any questions, it's like now's the time to ask. Okay. Yeah, so this is one way of defining a sequence. So we're defining a general rule to A sub n for this one, but you can have other kinds of sequences, right? You can also have what are called recurrence relations, which in computer science is going to be the more typical sort of sequence that you're going to be looking at, right? In the sense that, like, usually you're going to be defining sequences in computer science via for loops. And so when you're defining a sequence via for loops, you're usually going to be defining some sort of rule for your nth term in terms of previous terms of your sequence, which is what's called a recurrence relation. So definition, a recurrence relation for the sequence A sub n is an equation that expresses A sub n in terms of one or more of the previous terms of the sequence, namely in terms of A0, A1, A2, up until A to the n minus 1, for all integers n, where n is greater than or equal to n sub 0. And then we'll talk about solutions of these recurrence relations, maybe in class on Monday. So a sequence is called a solution of a recurrence relation if its terms satisfy the recurrence relation. So there's two examples on the next page where I talk about solutions to recurrence relations, but I just want to go through an example of like how you actually find the terms of recurrence relation. And then I kind of want to move on to sums, so that way I can ask questions about the sums on the exam. And so this is maybe the most famous example of a recurrence relation. So it's known as the Fibonacci sequence. So the Fibonacci sequence begins at the 0th term, A0, and then it goes on infinitely. It's defined by the initial condition A0 is equal to 0, and then A1 is equal to 1. And then once you know these two initial conditions, you can determine what the next term of the sequence is going to be by taking a sum of the two previous conditions or the two previous terms. So if I wanted to know what A sub n is going to be, you take the previous term and you add it to the second most recent term. So you take A to the n minus 1, and then you add to it A to the n minus 2 for any number n. So this goes on forever. You can always take a number and then, or take two terms and then add them together to get the next term and then continue the sequence forever. So this is an infinite sequence. And so we'll go through a couple of examples where we go through the Fibonacci sequence up until A6. All right, so A2, by definition, we have that A2 is going to be the sum of A1 plus A0. So this is going to be equal to A1 plus A0. We're told in the beginning that A0 is equal to 0 and A1 is equal to 1. So this is equal to 1 plus 0, which is equal to 1. And then you just follow this process. I mean, you've already gone through one example, so maybe going through like 5 more is a little bit tedious. But just to illustrate what's happening here, if we want to know the third term, we then do A2 plus A1. So you take the two previous terms and add them together. So we had A2 was equal to 1. A1 was equal to 1, so this is equal to 1 plus 1. This is equal to 2. I don't know if I'm going to go through every single one that I listed out, but this is equal. Yeah, so this will be equal to 2. A4 is equal to A3 plus A2. A3 was equal to 2. A2 was equal to 1, so this is equal to 3. So this is equal to 2 plus 1, which is equal to 3. Maybe I'll stop at A5. I feel like people are getting the idea. So this is A4 plus A3, right? We have A4.
On A5 and A6.
Yeah, so A4 is equal to 3. A3 is equal to 2. You add them together, you get 5. And then I guess A6, just for completeness, this is going to be equal to 5 plus 3, which is equal to 8. I didn't want to write it out in full detail, but you can keep on going, right? You just take the two previous terms, you add them together, and that'll give you what the next term is going to be. So that's the Fibonacci sequence. This is the most fundamental example for recurrence relation. You'll see other examples. There's some on the exam review. But they all kind of play out in the same way with varying levels of complication. Any questions about this example? Yeah, hopefully this is kind of, I mean, if it's boring, then that means you understand it and it's good. I think the next page, we'll focus on these next two examples in class on Monday. They're important to go through, but in the interest of time, like I want to make sure I cover at least summation notation. That way I can include it on the exam, which might not be a popular decision, but I'm going through with it. And so I'm going to skip these next two examples. And so now we're at the bottom of page 7 of the notes. This is a really important ability that you need to have in this class, and that is matching patterns to sequences. So maybe on the exam or sometime in the future, I could ask you, or I could give you like a sequence of numbers, and then I could ask you to find a general rule that determines like what the general term of the sequence is going to look like, or what the general pattern is going to look like. So a common pattern or problem in discrete math is finding a closed formula for like a recurrence relation or some other type of general rule for constructing the terms of a sequence. So sometimes only a few terms of a sequence solving a problem are known, and the goal is to identify what the sequence is going to be regardless. So even though the initial terms of a sequence do not determine the entire sequence, usually knowing the first few terms can help you make an educated conjecture about whatever the identity of our sequence is going to be. So this next example is maybe a little bit unorthodox. I'm probably not going to ask you something like this in the future. But say I give you some sort of sequence of the following nature. If I wanted to, I should say, this should be the word produce and not product. And so this is like, how can we produce the terms of a sequence if the first 10 terms are going to be like 1, 2, 2, 3, 3, 3, and then 4, 4, 4, 4. Can anyone tell me like what would be the next terms in our sequence? Or what would it look like? Yeah, sure.
5, 5, 5, 5, 5, because from what I understand, what you've seen so far, it appears to be on a pattern of where every number is listed in the sequence with the amount of terms that are that number. The what are being with an number n being used at an n terms because of how it's been like there's only 1, 1, 2, 2, 3, 3s, and 4, 4s in the exam in the starter 10 terms.
Yeah, exactly. So like the idea is whatever your number n is going to be, that number is going to show up n times within the sequence, right? So the number 3 shows up 3 times in the sequence. The number 4 shows up 4 times in the sequence. So the number 5 is going to show up 5 times, 6 will show up 6 times, 7 will show up 7 times. That's, I mean, at least that's the pattern that's established here, right? Maybe they throw a curveball. Maybe the 11th or the 12th term ends up being like 10 billion or something like that, and then we're off. But this seems to be the idea behind the sequence. Any questions about this example? Okay, this is the more, like this next example is the more typical kind of example that you would see either in like a calculus class or in this class as well. So for this example, it wants you to find formula for the sequences with the following first terms. So maybe I'll go through this a little bit quickly. I'm going through this so slowly. I must be like yapping too much. This is, so we'll go through this first example. So can anyone tell me what defines, like if I wanted to define this sequence, say it's like A sub n, what's the general rule for this first sequence? Does anyone see? Like how could we kind of concisely define what the sequence is? Oh yeah, you're raising your hand. Yeah, like what we're doing is we're starting with 1, multiplying by 1/2, and then the next term we're multiplying that by 1/2. 1/8 is 1/2 of 1/4, 1/16 is 1/2 of 1/8. So one way of writing this is you can say that A sub n is given by 1 over 2 to the nth power for n greater than or equal to 0. right? So if n is equal to 0, this gives you 1. It would be 1 over 1. If n is equal to 1, that gives you 1/2. If n is equal to 2, that gives you 1 over 4. Right, so this general n term can be written as 1 over 2 to the n. If I wanted to define the next sequence, so we start with 5, and then we have 11, 17, 23. What's the general rule here? What's happening?
Each term is I think is a of n is equivalent to a of n minus 1 plus 6.
Yeah, exactly. So you can define, instead of writing it in set notation, we can write it like this. So this is going to be equal. So I'm defining this as b sub n just to change notation up a little bit. This is equal to whatever the previous term is, and then you're just adding 6 to it, right? So the first term was 5. To get the next term, we add 6 to get 11. The next term is obtained by taking 11 and adding 6, so on and so forth. Where the first term is equal to 5, right? We have to specify the first term is given by 5.
It would be, I'm assuming part 3 would be c of n.
Oh yeah. So does anyone see what this pattern is going to be?
I believe I do.
Let's give other people a shot, unless no one wants to. Yeah, you can go ahead. Yeah, exactly. So there's kind of two different ways of thinking about this. The main idea is we're taking -1 and we're raising it to some power n. So that way it's going to be alternating. The main observation is that if n is going to be even, -1 is going to be 1. And if n is odd, it's going to be -1. And so there's two different ways, or there's more than two ways, but two kind of popular ways of writing this out. You could do -1 to the nth power, where n is greater than or equal to 0. So that way you have -1 to the 0th power will give you 1, and then n is equal to 1 will give you -1. Or you could do -1 to the n plus 1 power, and then you can start at n is equal to 1. Like either of these would work. The answer volunteered was n plus 1, so I'm going to leave it like this. But the main point is like the first term has to be 1. So that means whatever your first number you plug in, like there has to be an even power here. Yeah, question.
Can you also do -1 times n c n minus, like to multiply to take the opposite of the previous number?
Oh, that's true. Yeah, you can definitely do that as well. You could think about it multiplicatively. That's like another way of kind of writing out the same thing. So you could write this out in terms of like c to the n minus 1 times like -1 or something. Okay, any questions about this example? Okay, so yeah, I got the summations. This is what I wanted to get to. I don't really have a lot of time to talk through it. I don't know. It's kind of, I don't really like going fast when doing this because I feel like I'm not explaining things so great. But now that we have sequences, the main reason we're talking about sequences is so that way now we can talk about summing up terms of a sequence. So we introduce summation notation. So we begin by describing the notation to express the sum of the following sequence. So if you have a sequence a sub m up until a sub n, we can define the sum of the terms of this sequence using the following notation. So when you see this is sigma. This is like big sigma here. If you see this like sigma of a sub j, where j is equal to m, and then on top you have this n, this means we're representing the following sum. So the first term of our sum is a sub n, a sub m. That's why we have j is equal to m here. This means this is the first start, or the first index we're starting with. And then the n on top means that the final index is going to be given by n. And then this just means that we're adding every single term whose index is between m and n. So these are two equivalent notations. They mean the exact same thing. The idea is this is much more concise. It says everything that you need to know within like a little bit of space here. So here, the variable j is called the index of the summation. The choice of the letter j as the variable is arbitrary. So we could have used any other letter, such as I or k. And so this is what I was saying before. The index of summation runs through all integers, starting with its lower limit m and ending with its upper limit n. And then, as I said before, this is the letter sigma. It's used to denote summation. So it's worth noting that the usual laws for arithmetic apply to summations. So what do I mean by this? Is if you have a summation of the following form, you can think of distributing the sum throughout this smaller sum here, and then you can pull out terms that aren't part of the sequence outside of the sum, right? So it's almost like we're multiplying this sum to the terms of our sequence xj, and then we pull out the a in front. You can pull out the b from the sum, and like you're distributing the sum to the y sub j. This is what's called like linearity. Man, I really wanted to go through an example, but I think it's more important I pass back your homework assignments and your quizzes. So I'm gonna stop here.
Speaking of homework, it was homework